Let's record this. All right. Ready to start with probability? Can you hear me properly, by the way?
Yeah, okay.
Okay. So, I'm gonna be explaining this kind of verbally almost, maybe doing some problems in the middle, but most of this is gonna be like practice based. It's not a difficult chapter. The more in-depth chapter of probability is gonna be in the second book. It'll be in a separate class. So the first thing is experimental probability. Okay. So experimental probability is basically when you do an experiment a bunch of times, we call it trials. If we do a bunch of trials of an experiment, we can find out the experimental probability of something happening. What do I mean? For example, if you toss a coin 1,000 times and you record that 623 of those times heads pops up. Okay. So you tried an experiment 1,000 times and you got a heads exactly 623 times. The experimental probability of getting a heads therefore would be 623 over 1000. This is called experimental probability. As you can see, it's not equal to what we expect. It's not equal to 0.5. The reason for that is experiments are not perfect, right? So you might just be a very unlucky person for you to get so many more heads than you should have, right? You should have gotten about 500 heads. But that does not mean that the coin is conscious and it's choosing to give you more heads. It just means that, well, you're essentially unlucky. Okay? So experimental probability is not always the exact theoretical probability of something happening. Regardless, this is how you find it. Number of times the thing you are asking the probability of occurs divided by the total number of times you tried. Okay? Now, notation is important. If you say that P of A, this represents the probability of A happening, then we say A complement. This means the probability of A not happening. Complement means not. Okay? So A complement means A not happening. Okay? Now, a very important rule is that if I tell you that the probability of A happening is 0.2, then you can automatically tell me that the probability of A not happening will be 1 minus 0.2, always. Okay? So the probability of something happening and the probability of something not happening are always bounded by this very specific relationship. Okay? 1 minus something happening will be something not happening. Okay? Is that clear?
Yeah.
Perfect. Next up, we have so experimental probability is also called relative frequency. Don't get thrown off by that wording. It means the same thing. Okay. Either way, the number of successes divided by the total number of times you tried is the experimental probability or the relative frequency. Okay. So for instance, let's look at question number 1. It says that we threw a die a bunch of times, and this person, Heidi, believes that the odd numbers pop up more often than even numbers. So she tried to toss the die 10 times. When you toss the die 10 times, you get an even number in the first try, an odd number in the second, odd in the third, even in the fourth, and so on and so forth. Draw a relative frequency diagram. This is pointless. You're never going to be asked to do this in the exam. However, you can find out the probability of getting an odd number by just calculating how many times did you get an odd number? 1, 2, 3, 4, 5, 6, divided by how many times did you try? 10 times, which means that the probability of getting an odd number is 0.6. What do you think it should be in a regular die, a six-sided die? What do you think the probability of getting an odd number should be?
3, no, 10.
Sorry?
3 over 10.
3 over 10? No.
No,
It should be 0.5, 50-50, no? Because there's exactly as many even numbers as odd numbers. Like logically
oh yeah.
speaking, not even mathematically. It should be 0.5. So this does look like the die is biased towards odd numbers. But do you think that this experiment is, kind of bad? Do you think it can be improved? Why do you think this number might not be representative? Why do you think that, this might not be accurate? Any idea?
Because there's an even amount of God and even the person to die.
Well, no. So this experiment specifically, I mean, you're right about the result being wrong because we expect it to be zero point 0.5. But why is the experiment not telling us the right answer then? It's not telling us the right answer because I'm being too impatient. Only 10 trials to for a dice to show me that it's accurate. That's not enough. You might have just gotten unlucky, right? Sometimes you get three ones in a row. That's also possible. That it doesn't mean that the die is biased towards getting ones. It just means that you're unlucky or lucky, I guess, depending on the game. But regardless, the reason that this experiment cannot conclude anything is because you did too few trials. You need to do like 1,000 trials for you to start seeing the actual bias. Okay, is that clear?
Yeah.
Because like if this is the case, if this is accurate, then why don't I toss a coin two times and I accidentally get two heads and I claim that this coin will always give me heads? Isn't that very monkey brain of me? It is,
Yeah.
right? Because you're not trying enough times. You're not giving the poor coin a chance. So the point is, experimental probability is often going to be wrong unless you do the experiment inhumane number of times. This is where our best friend theoretical probability kicks in. Theoretical probability says that, okay, so first of all, if in an experiment all the possible outcomes are equally likely, okay, so for example, in a die, naturally, logically speaking, all the outcomes are equally likely. You can get a 1 with the same probability that you can get a 6, right? We call this a fair die. If you do a fair experiment where all the outcomes have the same probability, then the probability of any one of the outcomes happening will simply be how many ways are there to get the outcome that you want divided by the total number of possible outcomes that you can get. What do I mean? For example, if you roll a die, how many ways can you get a 1? What do you think? How many ways are there on a die to get a 1 when you roll it once?
All over six.
No, no. Yeah, you're jumping ahead, but yeah, basically. So there's only one way to get 1 on the die. There's only one way to get 3 on the die. There's only one way to get any number on the die. So 1. And how many total outcomes are there? 6. So that is the probability of getting 1, 2, 3, 4, 5, 6, any one of those things on a die. And that's how theoretical probability works. Similarly, if a fair die is rolled, what's the probability of getting a prime number? How many ways can you get a prime number? 3. You can get a 2, a 3, or a 5. That's the only prime numbers you can get. So the probability of getting a prime number is simply the number of ways you can get a prime number, which is 3, divided by the number of possible outcomes there are, 6. So that is your probability of getting a prime number. Now, remember, this is a very important rule. For any event in the world, the probability of something happening will always be a maximum 1 and minimum 0, never beyond this range. 1 means that it's 100% going to happen. 0 means that it's never going to happen, but it'll never be beyond these values. I've already explained this idea to you, but remember that if you know the probability of something happening, you can find the probability of something not happening by just doing 1 minus the probability of something happening. So this is an extremely, extremely useful result. Next, we have expected frequency. So basically, the example scenario would be if I roll a die 60 times, how many times do I expect sixes to pop up out of 60 times? To find the expected frequency of something or expected number of times something will happen, simply multiply the number of times you're trying with the probability of the thing happening. You will get how many times you expect the thing to pop up. Okay? Is this clear?
Yeah.
Perfect. So for instance, they haven't really shown an example here, but as I said, the expected number of sixes if you roll the die 60 times is 60, the number of times you're trying, multiplied by the probability of getting a 6, which is 1 over 6. That gives you 10. So we expect that we'll get about 10 sixes. Okay? It's basically the average of what we expect to get. Next up, we have sample space. So Sample space is basically a diagram or a set or a way to describe how many possible outcomes are there. Okay? So for example, if you're rolling a die, it's very easy to say that the possible outcomes are 1, 2, 3, 4, 5, 6. Okay? But this is not like listing down your outcomes is all not always the best way to do it. Okay? Because it can make life very difficult for you if you have too many outcomes, right? You'll have to make a very, very big list. So there are multiple ways to show your sample space. For example, a two-way table, something like this. So this table gives the number of boys and girls who wear glasses in a class. Copy and complete the table. Let's read through this carefully. Okay, so now how to read this table is very important. Look, this box will tell you the number of boys that wear glasses. 6 is the number of girls that wear glasses. 10 is the number of boys that wear no glasses, etc., etc. What does this mean? This means the total number of boys and girls, glasses and no glasses, basically the entire sample space. Okay. What is this number? This is the total number of girls. What will this number be? This number will be the total number of boys. Okay. So you need to be able to read this table very easily. Okay. Now we can find this missing box. How? If the total number of everybody is 32, okay, then this must be 32 minus 18 because this need to add up to 32, right? So that means that this is whatever is left over from 32 if you remove 18. You see what I mean?
Yeah.
So 32 minus 18 gives you 14. Okay. So now if you know this, then you can actually find out what this is because as I said, if you add up this whole row, you will get this. So what do you think this will be?
4.
4, because 4 plus 10 is indeed 14. Okay, good. So now that you know 4 and you know 6, you can also find out what this total will be. Because when you total all of this, you'll get this one. What is this going to be?
10.
10. Now, if you total all of these, you should get 32. So what should this be?
22.
22, because 10 plus 22 is 32. And finally, there's so many ways to calculate this guy. Can you figure out what this is?
12.
12, because 10 plus 12 is 22, 6 plus 12 is 18. That's basically it. So you can fill a two-way table by using this method. Now, what's the trick? There's one simple trick. Look for any row or any, oops, look for any row or any column that contains two things. You see, this column had two things. That's why I knew that I can find out this guy. Or, in general, find out any row or column that has only one missing thing. Okay? Because the goal is that every row and every column must add up. So this has to add up to this. This has to add up to this, and so on. So I saw that this column has only one missing thing, so I targeted this first. Once I found this, I saw that this row has only one missing thing right there. So I found this next. And then I see this column has one missing thing, so I found this. And then I found that this row has one missing thing, so I found this. And then finally I found this. Now, finally, maybe we can put all the numbers back here. Okay. So if a person is picked at random, what's the probability that it's going to be a boy without glasses? Remember that the total number of people is 32. Okay. So what's the probability that the person will be a boy without glasses?
10
Uh,
over 32.
exactly, because there's 10 people that are boys with no glasses, and there's 32 total. Now, given that a girl is picked at random, so we're only talking about the girls now. Okay. We're only talking about the girls. What is the probability that she does not wear glasses? Now, what do you do in this case when you're only talking about a specific set? Ignore everything in the table and only look at this row. Why? Because we're only talking about girls, right? So how many total girls do we have?
18.
18. That's 18. Total girls is 18. And how many girls do not wear glasses?
12.
So 12 over 18 is your answer for if a girl is picked, meaning we are locked in on this row only. What is the probability that she does not wear glasses? 12 over 18. That's it. Now, what is next? Yeah, so basically just questions. So I'm gonna leave you with some